So one neat application of eigenvalues and eigenvectors pertains to what's called dynamical systems and a little bit of probability. One classic application problem, they usually all sound the same after a while. Here's one. We have a remote island resort. It receives radio broadcasts from two radio stations. Let's say one's a news station and the other one's a music station. And we're told that of the listeners who are tuned into the news station, 70% will remain listening to that news station even after a commercial break or a station break. And let's say that station breaks occur every 30 minutes. We're also told that 30% will switch from the news station to the music station at that station break. And from the perspective of those who are already listening to the music station, those listeners who are tuned into that station, 60% will switch to news during a station break, and 40% will remain listening to the music station that they were already tuned into. And let's suppose that everyone on this particular resort island is listening to the news at 8:15 in the morning, which stands to reason. I guess people logically start their day listening to some news first to see what's going on in the world. But here's the focus question we want to look at. What percentage of the listeners will be listening to the music station at 9:40 a.m.? Now, 9:40 a.m. is an interesting time. It's after the first two station breaks. If we look carefully, we're starting our time count at 8:15 a.m. We know that the station breaks or commercial breaks occur every 30 minutes. So the first station break will occur 30 minutes after 8:15 or at 8:45. And then the second station break will happen 30 minutes after that, or at 9:15. And if we were to push it to a third, 30 minutes after that would be at 9:45. So if we ask what's happening at 9:40, we're right before the third station break. So we're well into what happens after the second station break, and that's why we're focusing on that time. We want to just see what happens after that second station break takes effect, if you will. So we're going to capture all these probabilities that were given to us in the opening problem using a matrix P. It's going to help us transition from one station break moment to the other. And if you look at matrix P, you could kind of tell what the columns represent, what the rows represent. In column 1 of matrix P, I have 0.7 and 0.3. Well, those are decimal equivalents of 70% and 30%. And remember what 70% and 30% really were referring to. It means that after the first commercial break or station break, 70% of the people who were listening to the news station would stay listening to the news station. And 30% would switch from news to music. So if we look at this matrix and we label across the top of the columns, if we call the first column the news column, no pun intended, and the second column the music column, and again we look at the first row again meaning news and the second row meaning music, we can see that we have this correlation with the probabilities here. So going down column 1, let's see if we can make sense of this. Going down column 1, if a person starts at the news station listening to the news already, and then a station break happens, what's the likelihood that they'll stay listening to the news? Well, we're told if a person starts at news and winds up still staying at news, so in position 1-1 we're at news to news, that's a 70% chance. But what is the other likelihood? Someone could start listening to news and switch to music, and there's a 30% chance. Okay? So look at the column perspective, saying, well, where are you now? And going down the column, what's the probability if you'll switch to someplace else, or stay the same, or go someplace else? Let's look at that from the music perspective. Let's say someone's listening to the music station. What's the likelihood or the probability they'll switch to the news station? Well, we're told that was 60% in the given. So going from music to news at a station break, 60% chance of that happening. And the likelihood of someone listening to music and then staying listening to that music station after the station break, music to music, is a 40% chance. So I hope that gives you a better understanding as to how a matrix can capture all these probabilities. And now we're going to throw a little vocabulary at you. We're talking really about a regular stochastic matrix. And a regular stochastic matrix refers to a square matrix P whose column vectors are probability vectors. What's a probability vector? Well, it's easy to tell. The columns add up to what all the probabilities have to add up to with an event. All the ways that an event can occur, if you add up all those probabilities, they have to add up to 1. So you could clearly tell this is a stochastic matrix because 0.7 and 0.3 add up to 1, 100%. And in the second column, 0.6 and 0.4 add up to 1, or 100%. But a regular stochastic matrix means not only do you have the column vectors as probability vectors adding up to 1, but itself has all positive entries. So we could tell that this is a regular stochastic matrix because all these entries are positive. Now, that's not to say you can't have a stochastic matrix that has a zero entry, because regular stochastic matrix also refers to a matrix if you have a positive power, say p to the k, where k is positive, and then you wind up with all the entries of that p to the k matrix being non-zero, actually positive, then you have a regular stochastic matrix as well. The neat thing about regular stochastic matrices, as we're about to see, is when you use them to predict what's going to happen in the future, far down in the future with regard to these outcomes, it will settle down to what's called a steady state or an equilibrium. So let's see how we get there. So again, we're looking at this basic question still. We want to see what happens in the long run, supposing that everyone's listening to the news at 8:15 a.m. Just a little bit more vocabulary for you. A state vector. A state vector lists the probability of n possible outcomes. In this case, we have 2 possible outcomes. Someone could be listening to the news. Someone could be listening to the music station. So those are the 2 outcomes at any given time. And in this case, the probabilities that a person picked at random will be listening to the news station or the music station is what the state vector will capture. So a state vector is going to be a column vector listing probabilities of the outcomes, probabilities of or the likelihood of someone listening to the news or someone listening to music. So here's a question. Can you identify the initial state vector for this problem? Here's the hint. Consider t equals 0 to represent the time when people are listening to the radio station at 8:15 a.m. Now, what were we told about how many people were listening to the news station at 8:15 p.m.? Let's see. We were told that everyone's listening to the news station at 8:15 a.m. So if you think of that state, if you were thinking of a column vector of probabilities, and you wanted to capture the fact that everyone at that particular time index, say t equals 0, corresponding to 8:15 a.m., if you wanted to say that all of them were listening to the news station, well then what would the probability be in the first position for the news? What would the probability be in the second position for music? Well, if you said 1, 0 as a column vector, you're correct, okay? Because the first entry of this probability vector represents the likelihood of someone listening to the news at a particular time, and we're talking about time index 0. And the second position refers to the probability of someone listening to the music station. But since we were told everyone was listening to the news station at 8:15 a.m., it's appropriate to have 1 and 0. 1 plus 0 is 1, definitely a probability vector. Okay, so again, at 8:15 a.m., the probability that a person picked at random is listening to the news station is 100%. Another way to say that is 100% of the people on the island are listening to the news at time index 0, namely 8:15 a.m. But now let's explore what happens as we move forward in time throughout the day. How do we compute the state vectors, for example, after the first station break, after the second station break, which we could refer to x vector at 1 and x vector at 2? Well, we already know what happens, or how to represent the state at time index 0 at 8:15 a.m. How can we use our probability information that we capture in this matrix to predict what's going to happen after the first station break? Well, let's multiply it out. If we're trying to get the state vector after the first station break, and we'll call the components of x vector 1, we'll call it x sub 1 of 1 and x sub 2 of 1, how do we compute those elements? Well, we know that if someone starts watching the news, there's a 70% chance that they'll continue just to listen to the news after the first station break. So again, if someone's listening to the news to start with, after the first station break, there's a 70% chance they'll continue to listen to the news. So if you have 100% chance of everyone listening to the news as they start the day, then 0.7 times that 100% will tell you how many, what's the likelihood or what's the probability that people will still be listening to the news after the first station break. And then let's think now, in this entry, from music to news, people switching from the music station to the news station, that would be 0.6 times how many people were listening to music. Well, actually no one was listening to music in the beginning, so 0.6 times 0 is just 0. So we have 0.7 representing the likelihood that someone chosen at random will still be listening to the news after the first station break. And getting the music perspective now, let's see, how do we get this? Well, you'll notice we have these entries. So someone goes from news to music, news to music. Well, 0.3 chance of going from news to music. Well, how many people were listening to the news? That was 100% of the people. So now we go 0.3 times 1 gives us 0.3. And how many people who are listening to music will stay listening to music? 0.4 times the second entry. Of course, that second entry was 0, so we just capture 0.7, 0.3. And of course, we would expect 0.7 and 0.3 to be the answers or the state of the X vector after the first station break, because everyone was listening to news to begin with. So those percentages that we were given earlier would just directly correlate to what happens after the first station break. So point being made here, we now know that after the first station break, we're using this probability vector, this state, to represent what's going on. 70% of the people, if you chose them at random, will be listening to the news, 30% to music. Well, how can we use that to go forward? Well, it's now possible to take this result and apply the same probability structure that we were given and start here instead. So in order to get x sub 2, that is, what happens after the second commercial break or station break, we just multiply these same probabilities out. So from going from news to news, right? Well, we already had 70% to start with listening to the news, and there's a 70% chance that they would continue to listen to the news. So 0.7 times 0.7, as you're accustomed to using the word and in probability, means multiply, right? And then as you go 0.6 from music to news, well, we did have a 30% chance, or 30% of the population already listening to music. So 0.6 times 0.3. 0.6 times 0.3. Listening to music to begin with, and then switching, right? And probability of switching from music to news gives us the extra piece that we need to make the component as to how many people are now listening to the news, or what percentage of people are now listening to the news after the first station break. And do the same thing again with your second row. 0.3 times 0.7, 0.4 times 0.3, multiplying those probabilities gives you now the likelihood, if someone was chosen at random after the second station break, what's the likelihood that they'd be listening to music? It would be 0.33. These decimals probably seem familiar to you. You might be thinking about 2/3 and 1/3, and we're going to see that that's actually going to be the case in the long run with this particular stochastic matrix. But I just want to take a closer look at those calculations we did a moment ago. Maybe you noticed something about this structure. Matrix multiplication indeed was being modeled there. Okay, it's a great application of matrix multiplication. And maybe you see a column style going on here. You can certainly look at it that way. But the main point is to get what's happening, right? To get the state after the first station break, you take your transition matrix P and you multiply it by the state, the initial state at time index 0. And that gives us 0.7 and 0.3. Those are the calculations we did. It's the same thing as matrix multiplication. And then to get the second state, x vector at time index 2, we could do the same thing. We multiply the first state, x sub 1, x vector of 1, times that transition matrix P, and we'll get those values that we had before. Okay, so we have a little bit of repetitive calculations going on here. You could realize for a second now, if you look at this closely, since x2 is nothing more than the transition matrix P times x1, but wait a minute, x of 1 was transition matrix P times x sub 0, then we could have concluded, well, wait a second, we could have multiplied x sub 0 times P squared if we wanted to. In fact, you can say that the next state, x of k plus 1, is simply equal to the transition matrix P times the previous state, and that's sometimes denoted this way. X sub k plus 1 equals P times x sub k. And then, of course, noticing that we're just multiplying by the same matrix P over and over again, starting with that first initial state, you don't have to actually figure out all the intermediate states to jump to any particular state that you want. You can just take your transition matrix P and raise it to that positive exponent and multiply it by the initial state to get any other new state that you'd like. It's a neat shortcut. So let's imagine what will happen. I chose 48 because there are 24 hours in a day, and it stands to reason there'll be 48 commercial breaks if you go around full cycle. And where would we be at that point? That is, what would be the likelihood of someone listening to news and music after 48 commercial breaks or station breaks every half hour? Well, if you actually take a calculator and multiply it out, it's very easy to do. You just use your calculator's exponential feature, and starting with that initial state, right? 100% of the people watching the news, and no one watching, or 100% of the people listening to the news, I should say, and no one is listening to music to start their day. It really does look like it's settling at a steady state, as we say, or equilibrium. It's settling down to 2/3, 1/3. That means there comes a point where if you're at this stage, you could keep on applying your stochastic matrix P, and it's really not going to change this thing. It's going to just settle down to that location. And again, I've been using this term, and now we're going to formally define it. A steady state vector for a regular stochastic matrix P is a probability vector Q such that P times that Q vector, that probability vector, results in Q. It doesn't really change because it's settling down to this equilibrium, if you will. Now, for a linear algebra student, this statement right here should look very familiar. Do you remember what it's saying? Maybe if you think of the number right in front of the Q, right? How many Qs? 1, right? This really turns out to be an eigenvector with an associated eigenvalue of 1. And that's why this is a wonderful application after you study eigenvalues and eigenvectors to see it in action with an application process. So again, if we test our hypothesis, if you actually take 2/3, 1/3 as your probability vector, multiply it by this regular stochastic matrix, lo and behold, you get the same thing exactly, 2/3, 1/3. So we are quite confident that Q is the steady state vector that we're talking about here. It is the eigenvector associated with lambda equals 1. But another way to show it is to go back to your study of eigenvalues and eigenvectors and actually use your characteristic equation, set it up, right? Starting here, you know that means the identity matrix minus the stochastic matrix times Q must equal the 0 vector. Well, how does that look in this case? Okay, so identity matrix 2 by 2, here it is. The stochastic matrix that was given to us, here it is. The components of Q vector, we'll call Q1 and Q2. 0 vector is the column vector 0, 0. So let me check here if I got the right subtraction. So 1 minus 0.7 is 0.3, 0 minus 0.6 is negative 0.6, 0 minus 0.3 is negative 0.3, 1 minus 0.4 is 0.6. Looks good. I create an augmented matrix and put in the calculator, reduce for echelon form, gives us this. So we have one free variable, rank is 1, one free variable, and we'll let that second variable Q sub 2 equal the free variable S. We'll lose a parameter S. So we now have a family of eigenvectors. Q vector equals 2S S. But we want to realize that, wait a minute, it's not just any eigenvector from this family we're interested in. Keep in mind, what has to be the case about 2S and S since we're talking about a probability vector Q? Remember, probabilities describing an event, all those probabilities added together cannot exceed 100% or 1. So that means that if 2s plus s equals 1, 3s equals 1, s equals 1/3, bam, voila. Q equals 2/3, 1/3 as our probability vector, or our steady state vector, our equilibrium vector for this particular stochastic matrix and situation. So again, our suspicions were correct. Okay, we have, in the long run, we tried it out. We did a whole day of commercial breaks, station breaks, and it seemed to be honing in or settling down to 2/3, 1/3. Then we went through testing that hypothesis with actual column vector of 2/3, 1/3 seemed to settle there. And now, of course, we have the eigenvector eigenvalue proof, where we were able to show that, yes, that indeed has to be the steady state vector we're talking about. So that means in this particular problem, late in the day, we would expect 2/3 of the listeners on the island to be listening to the news, and 1/3 of the listeners on the island to be listening to music. Or put another way, if you were to randomly select someone on the island, there would be a 2 in 3 chance that that person was listening to the news, and a 1 in 3 chance that the person was listening to music. And this type of analysis is, or application, is referred to as Markov chains, in honor of Andrei Andreevich Markov, who was the first to apply this. A poet, loved poetry, and you probably would be intrigued to know that his analysis of matrix algebra could be applied to so many things beyond poetry and things like that. Of course, it begs the question, why are most people on this resort island listening to the news instead of listening to music? But I guess that's for another video. Thanks for watching, everyone. Stay safe.